Module 9 is the second of three modules concerning beams and the first that gets into design issues and is separated into two lessons. This lesson, Lesson 20, examines the design provisions for beams and other members subject to flexural stresses that are given in Chapter F of the AISC specification. The next lesson, Lesson 21, will look at design plots for beams as well as a review of the local buckling provisions for steel beams. As thoroughly discussed in Lesson 18, the nominal flexural capacity of a structural steel beam, M sub n, is based on the stress distribution that exists at the time a limit state has been reached. Four limit states are possible. The maximum possible moment capacity is defined by the yielding limit state and is given as the plastic moment M sub p, where the stress distribution is fully yielded or plastic. However, certain conditions may result in instability of the beam either globally or locally, and a lower moment capacity will result. This includes lateral torsional buckling, flange local buckling, and web local buckling. AISC Table F1.1 provides a summary of possible limit states for all types of beam sections. In CVN 446, we will concentrate on symmetrical cross sections. Shown is AISC Table F1.1. The design of beams, particularly welded beams with local buckling issues, can become complicated. This table points you to the correct sections within Chapter F. For the most part, we will be in Section F2 for this class. Slenderness parameters are defined for the three instability limit states for beams. The Greek lowercase lambda is often used for the slenderness parameter. The slenderness parameter for lateral torsional buckling is given as the ratio of the unbraced length to the radius of gyration about the weak or y-axis. Note that the slenderness parameters for both flange local buckling and web local buckling are the same as what we use for columns. Provided none of the instability parameters control, the nominal moment capacity of a beam is given by the plastic moment M sub p. We then say that the nominal moment capacity M sub n is M sub p. Each instability limit state has its own slenderness limit, lambda sub p, where the subscript p means that this is the limit for a beam to reach its plastic moment. Any more slender than that, and the moment capacity must be decreased. The design moment capacity is then obtained by multiplying the nominal moment capacity M sub n by a reduction factor of 0.90. Shown are the slenderness limits for the instability limit states. The lateral torsional buckling slenderness ratio is 1.76 times the square root of E over F sub y, or 300 over the square root of F sub y, making the substitution of 29,000 KSI for E. The slenderness limit used for local buckling are different from those that we use for columns. This is because the conditions controlling local buckling in a beam are not the same as in a column. For example, only half the web is stressed in compression in a beam, whereas the entire web in a column is stressed in compression. In a beam, the compression flange has the potential to reach level of F sub y, whereas in columns the stress is reduced below F sub y to F sub critical. These slenderness limits are given in Table B3-1b. As previously discussed, a cross-section that does not exceed either of the plastic local buckling slenderness limits is considered a compact section. A compact section can reach the plastic moment without buckling locally. However, lateral torsional buckling may still reduce the moment capacity. With the exception of a handful of shapes, most all W shapes are classified as compact sections. Page 16.1-47 has a user's note that lists the W shapes that are not compact. Sections that are not compact are classified as either non-compact or slender sections. Note that non-compact sections have an inelastic stress distribution at the time of failure, and slender sections have an elastic stress distribution at the time of failure. This class will focus on compact sections. Similar to the plot we used to define the two regions of behavior for columns, a generalized plot can be developed for beams. Here, the nominal moment capacity is plotted versus the slenderness ratio. Note that the response curve is now divided into three regions. Unlike a column, a beam can be fully yielded, hence the plastic region, in addition to the inelastic and elastic regions. Chapter F, Section 2 provides the design provisions for compact sections. Since there is no possibility of local buckling, their moment capacity can only be reduced by lateral torsional buckling. Here, instead of using the slenderness parameter, they move the radius of gyration over to the other side of the equation and evaluate the unbraced length with limiting lengths. Therefore, as long as the unbraced length does not exceed the limiting length for plastic behavior, or L sub P, the plastic moment is given, or the moment capacity is given by the plastic moment. Note that L sub P is just the slenderness limit we saw before, but now with the radius of gyration. When the unbraced length exceeds the plastic slenderness limit, L sub P, but is below the elastic slenderness limit, L sub R, the beam is in the inelastic region of behavior and its moment capacity is defined by an inelastic flexural stress distribution. L sub R, as defined by equation F-6, defines the limit between inelastic and elastic behavior, or the lower end of the inelastic region. This equation gets a little complicated due to all the terms that are in it. Note the presence of the 0.7 F sub Y term in the equation. This takes into account residual stresses, which are assumed to be 30% of Fy. Also, instead of using the radius of gyration about the y-axis, an effective radius of gyration is used, which is given as R sub Ts. This value is given in table 1.1-1 for the W shapes. This value differs from the radius of gyration about the y-axis, R sub y, and is less than R sub y. It's taken into account the reduced stiffness due to the flexibility of the web as the tension member, which is very stiff, tries to stay put. For a W shape that laterally torsionally buckles in the inelastic region, the nominal moment capacity is given by AISC equation F2-2. This equation is simply an interpolation function between the plastic moment and the moment defined by first yield with residual stresses. As discussed in lesson 18, this moment capacity is given as 0.7 times F sub Y times the elastic section modulus S. Another new term is C sub B, which is the bending coefficient. This coefficient actually increases the calculated moment capacity due to a favorable moment gradient, as will be discussed later in this lesson. It is important to note the upper limit on the nominal moment capacity is the plastic moment. The reason for this limit is due to the fact that the C sub B term can increase the calculated moment capacity above the plastic moment, which is not possible since the plastic moment is based on the fully yielded cross-section and defines the maximum possible moment capacity of a beam. AISC Table 3-2 provides useful information for W shapes and actually makes the use of equation F2-2 easier. The shapes are ordered according to the plastic moduli. z sub x from largest to smallest. The shape with the bold designation is the lightest section in its group. The table provides calculated values for phi m sub p, phi m sub r, L sub p, and L sub r. Note that the values are for a yield strength of 50 ksi. The table provides other values that will have more meaning in subsequent lessons. The AISC Steel Manual provides a simplified procedure for calculating the moment capacity of a W shape in the inelastic region, that is, where your unbraced length L sub B is between L sub P and L sub R. The term BF, which is given in Table 3-2 with a phi of 0.9 already applied, is defined as shown. Basically, the BF term pulls most of the constant values out of equation F2-2. These values do not change for a given W shape. These values are also obtained from Table 3-2. The design moment capacity is then calculated as shown. If the unbraced length is greater than L sub R, it means that the moment capacity is defined by an elastic stress distribution. The nominal moment capacity for the elastic region is derivable by calculating a critical buckling stress as given by AISC equation F2-3. This critical stress is then multiplied with the elastic section modulus S to arrive at a nominal moment capacity. Again, the nominal moment capacity is then multiplied by a reduction factor of 0.90 to get to the design moment capacity. Note that the square root term in equation F2-4 can be conservatively taken as 1 to simplify the calculation. A word of caution, though, is that this may result in the use of a much heavier beam section. In this course, we will not take this shortcut. The equation for the critical elastic buckling moment is derived assuming a constant moment along the entire unbraced length of the beam. This actually results in a conservative assumption, since in practice, the moment will seldom remain constant along the unbraced length. There's always some change in the moment between bracing points. This means that the compressive stress is not at a high level along the entire length of the compression flange, reducing the susceptibility of the beam to lateral torsional buckling. As shown in this slide, if the end moments or the moments at either end of the unbraced length are equal, the moment will be constant and there will be no moment gradient or change. However, if the moments are not equal, and say in this case are opposite as shown in the second case, a significant moment gradient exists due to the inflection. Note that in this extreme case, the compression flange is basically split in half between the top and bottom flange. This is like having two short columns, hence a higher buckling capacity. To take into account the increase in resistance to lateral torsional buckling due to a moment gradient, AISC equation F1-1 is used to calculate the bending coefficient C sub B. The terms in the equation are taken from the moment diagram between the bracing points or along the unbraced length. The moments with the A, B, C subscripts are the absolute values of the moments at the quarter points. The maximum moment term is the absolute value of the moment regardless of location, even if it is at one of the quarter points or at the end of the unbraced length. There is an additional term in the equation that is not shown, which is R sub n. Since we will be dealing with mostly W shapes in this course, which are doubly symmetric cross sections, its value is taken as 1. This slide shows graphically how the moment terms in the C sub B equation are determined. Remember, absolute values are used. When determining the quarter point values, it is useful to use the area under the shear diagram to determine the change in moment between quarter points. Note that it is conservative to assume C sub B is equal to 1, as this will result in a lower moment capacity. However, being too conservative will lead to more expensive designs. Table 3-1 on page 3-18 provides C sub B values for typical loading and bracing conditions. This is a good page to tab. Note that for a simply supported beam with a concentrated load at midspan, the value of C sub B is 1.30 without any lateral bracing except at the end supports. C sub B increases to 1.67 with a lateral brace at midspan, and the unbraced length is reduced in half. Both of these conditions result in a substantial increase in moment capacity, possibly enough to have the moment capacity based on the plastic moment, completely negating the issue of lateral torsional buckling. Looking at the response curve for a laterally unbraced beam, note that the effect of the bending coefficient C sub B on the moment capacity of the beam is to shift its response curve up by the magnitude of C sub B. Note, however, the upper limit on this increase is always the plastic moment. Again, at the plastic moment, the section is fully yielded and there is no more strength to give. This ends lesson 20.